Okay. Next, we're going to calculate these values. And it says something small here. There's a little instruction if spearmint is needed, but we don't need spearmint. So let's go ahead and begin our process of calculating. Slight differences from when we did it in class, because now we're trying to draw inference from it. But we are going to start just by filling in these data as we normally do. So let's take our degree of freedom for this particular mean that we're calculating is n minus 1. It's the sum of these two that ends up being the one we look up. We'll calculate our mean for x using the average function. And I'll just click in the top cell, hold Control-Shift down arrow. There we are. We'll calculate our sum of squares, so we have to subtract the mean. Thought about putting this into just one step, but we actually need to have a separate calculation of this deviation in order to get our z-score. And if you don't remember from last year, the formula for our R calculation is just the sum of z-score for x times z-score for y divided by n minus 1. That's the formula we're using for inferential statistics, which is a little different from what we were doing last semester. So I'm going to go ahead and stabilize it, and I'm actually not going to stabilize the row. That'll allow my copy paste. I mean to say I'm not going to stabilize the column. I will only stabilize the row. The column is not going to move. So we have our deviations. I'll go ahead and get our squared deviations right away. And then we're going to calculate the z-score. And so we're going on. Let's copy and paste these down. Oops, I lost some formatting there. I like my formatting, so I'm going to just copy these and paste down the formula using that fx. We can get our sum of squares now. Use the Control-Shift down arrow. Yep, works fine there. And we're going to estimate the variance. Last year, we just divided by n, but we are going to use our EVAR so that we can call these inferential statistics, meaning we're going to divide by df, just as we did in the t-tests. And our standard deviation is just the square root of our estimated variance. To calculate our z-score, you may recall, so let me write a couple of formulas here. First off, the Pearson R is just going to equal the sum of the z-score for x times the z-score for y divided by n minus 1. And so that's going to be the score for R that we're seeking. And remember how to get z. We're just going to the z-score for x or the z-score for y is just each score. So we'll start with x as an example, minus the mean for x divided by the standard deviation for x. And I realized just as I said that we need to change this to estimated standard deviations and just use that x. Okay, so here we're set with the formulas. Let's go ahead and get that done. We have the formula is x minus m for x, but we have calculated that right here in this column. So we'll just reference this column instead of typing a formula in again that we might make a mistake of. And we'll divide by our standard deviation. And I'm going to stabilize that row again. And then we can go ahead and calculate this down, and we can see we have our and here we can see that we have our z-scores for all of these. So just the scores in relation to what would be 0. And 0 as the mean of a z distribution. We can do the same thing over here. And let's start by just, might as well just grab all of these. They're going to come up as errors initially, but let's go ahead and paste everything in there. And we can go ahead and grab this also. All of this should come out fine, but of course we'll always, wise mathematicians that we are, will always double check. So there we go. And let's just take a look and make sure that this should actually say x minus m. This is actually our deviation column. So we'll go ahead and just take a check here. And it looks like it's 104, the right one, and that is the right one. So that's good. And let's just make sure that it got the standard deviation as the divisor. And one last thing, let's make sure that our sum of squares included all of the scores needed, and that is good also. So we're all set to get our cross products, Zx times Zy. So here's the column with Zx. These are our raw data, just to distinguish it in case we were doing experiment. Let's use our times sign and get Zy. And there's our first cross product. We just do the same thing for every single one. I'll paste the formula in. And so we're good there. Up here, we put our number of pairs. And the degree of freedom when we're doing this particular calculation is going to be this just -1. So there's a couple degrees of freedom in this problem. We sum up our Zx, Zy right here. And then our R score for our sample, the number that we're looking for most of all, I'll highlight it here, is going to be taking this and dividing by that degrees of freedom. So taking the sum of Zx, Zy and dividing by the degrees of freedom. And that's our sample score. And it looks like we have a 0.56, which is pretty close to what we were predicting. You'll see that we have a couple other things to do here. We've actually done these bottom two. We've already found out our alpha. So we won't even, I think I won't even put that there. We are going to need our R squared, and I'll talk about why in a moment. That is simply R squared, as the formula suggests, 0.31. So I'm going to take these three numbers and talk about them with you when we get up here. So 0.56 and 0.31. So first off, our R sample is 0.56, a moderate correlation. We don't have to do Spearman because we had a normal distribution. We are going to use that tool, but before that, I'm going to put in the 0.31 right here, which is the square of this. And then I'll talk to you about what this means. And let's use this tool to find out the probability level of getting an R score that high. Let me copy this down. And I'm going to click on the link to the tool. And here we are. We're going to go down. Here's Z, here's T, here's F. Now we're at R. So let's put in that 0.56. And the degrees of freedom, in this case, the one that we're going to use for entering right here is the number of pairs -2, which is 32. And we'll find the P. And it says the two-tailed p-value equals 0.0006. And so the way we're going to, it says this is extremely statistically significant. What we're going to do is let's put the p-value here. We don't have a less than right now, so let's just put p equals 0.0006. If we were going to state it as less than, we would find the nearest decimal place that it was linked to. So in this case, to state it as p less than, we would be saying p is less than 0.001. And that's the best we can do because we have the 6 there in the 10,000 place. All right, so with that said, we know we have a significant result. We have to reject HO, and we can describe this conclusion in two ways. So the first description is really easy. We can see that we have positive correlation. So there is a significant positive correlation between mindfulness and emotional stability. I'm going to shrink this a little. So, and emotional stability, and then we can put our R score. We just put our degrees of freedom 32 in here. We can put that R 0.56, and we can write now P is less than 0.001. You could also write P equals 0.0006. Either is okay. But we have to add one more thing. R squared is what we use to determine the explanatory power. We turn it into a percent. So we're going to turn this into 31% because that's what 0.31 is. And we can kind of put this into words, and it would look something like this. We would say approximately 1/3. Now I'm just saying 1/3 because I can see the 31% is close to 33%, or I might put almost 1/3. 1/3 of the variance in emotional stability is explained by the variance is explained by, let's just put is explained by mindfulness. And then I can just put here r squared equals 0.31. We don't have to write any significant there because we already did the significance test. So that's how you would go on and explain the r squared in this. I'm going to stop the video and make one more video to show about the 3 explanations.